Hello, Professor.
Hello.
Professor Trotta, you're muted.
Thank you for letting me know.
Mm.
All right, just brief recap. Forward bias characteristic is right here. Reverse bias characteristic is below. For an ideal diode model, forward bias simply means there is 0 volts dropped across the diode. And in reverse bias, it's 0 amps flowing through the diode. So in this model, we simply replace the diode with either an open circuit or a short circuit. So before we begin our analysis, we would make an assumption. We'd assume a diode state based on circuit conditions. You would either assume it's on or off. If it's on, we replace it with a short circuit. And if it's off, we replace it with an open circuit. Essentially removing the diode and replacing it with a wire, or not replacing anything. All right, and then open circuit between those 2 points. Make sense? Yes, questions? Yes. So this would be forward bias. This would mean it's reverse bias. Actually, that would be the starting point. Thank you for bringing it up. So the way we would use this model is we would inspect a circuit, and depending on the circuit conditions, we would, for lack of a better word, I would say guess. Okay, we would guess whether the diode is on or off, meaning whether the diode is forward bias or whether it's reverse bias. If we assume the diode is forward bias, we would make the assumption diode is on, and if it's on, replace with a short circuit. If you assume that it's reverse bias, then it's off and it's open circuit. So this model doesn't require anything except a substitution. So you take the diode out and you substitute with a short circuit or an open circuit. Hence the name ideal diode model. Another model is the constant voltage drop model. This is an extension of the ideal diode model, where we would take the 0.6 volts into account. Okay. And of course, we are referring to silicon or silicon diodes. So we take 0.6 volts. If we were working with germanium, or let's say gallium arsenide or gallium nitride, we would take 0.2 volts for germanium, 1.2 volts for gallium arsenide. So depending on the semiconductor we are using. For the most part, we are dealing with silicon diodes and silicon devices. So you would just say it's 0.6 volts. So a ideal diode model, voltage is 0 in forward bias. In a constant voltage drop model, we would model it as an ideal diode in series with a voltage source of 0.6 volts. Okay, 0.6 volts. And again, constant voltage drop, meaning the voltage drop across the diode is going to remain constant. Just a vertical line at 0.6. Okay, vertical line at 0.6. And so that is indicated right here on this characteristic at the top left. So V on would provide a constant voltage, hence we represent it as a voltage source because it's providing a constant voltage. So in forward bias, we would say diode is on and it drops 0.6 volts across its terminals. So the voltage source would represent plus at the anode and minus at the cathode. Okay, so the voltage source will have a plus at the anode and a minus at the cathode. And then in reverse bias, it's the same. You simply replace it with an open circuit. Yes. And so question being asked is, how do we decide which model we want to use, right? So I have a comparison of all the four analysis techniques on the next slide. And then I'll talk a little bit more about how we determine which model to choose. But so far, so good. Other questions? So let's see here. We had this circuit, right? This one. We have the single diode, Thevenin equivalent circuit with one voltage source and one resistor applying or supplying energy to that diode. So let's say I'm analyzing this circuit. Okay. So if I use the ideal diode analysis for that same circuit, I would simply make an assumption. And the assumption is because I have 10 volts applied here, and what's this 10 kilo ohm resistor, and my anode is connected in the direction of the positive end of the voltage supply. So logically, my assumption, my guess would be that the diode is forward bias and hence on. If it's ideal diode model, we would replace the diode with a short circuit wire. And now, circuit analysis techniques. We wish to find the current through the diode and or the voltage across that diode. So the verification for both ideal and constant voltage model would be when we calculate our voltages and currents, and then we match it with our assumptions and see if our assumptions hold true. Yes. So this is ideal diode for now. Constant voltage drop would be afterwards. This is the ideal diode model. So right now it's simply a short circuit. It's a constant voltage drop model. We'll add a voltage source in there. So if I analyze this, VD would automatically be equal to 0. It cannot have any other number, right? VD is 0. It's a short circuit. One assumption is verified. ID must be positive. ID is the diode current that flows from anode to cathode. So if you're assuming that the diode is on, then at the end of my analysis, I should have a positive number or a positive value for ID. If it's negative, that means my assumption is incorrect. And so if I analyze this circuit right now, the current is simply the current flowing through the resistor, and ID should be equal to 10 over 10K. Positive 1 milliamp. right? Positive 1 milliamp. Oh, I just realized I'm doing it on the slide for the constant voltage drop. Let me cut it out. Okay. Let's do it here. Okay, so that's at least one assumption verified, right? Voltage drop VD is 0, current ID is positive. So taking these two into account, verified. And here the assumption is D is on. But let's say I assume that the diode is off. If I assume diode is off, then VD must be negative. That's the condition. VD must be negative. Current flow should be 0 and VD must be negative, right? Characteristic. So if we assume diode is off, diode voltage must be negative. If you obtain a positive value, or if you obtain a forward current, that means our assumption would be incorrect. In this case, it'd be rather straightforward to analyze. Plus minus, and my diode voltage is measured in this direction. What is the value of VD? So I'm assuming that the diode is off, but the diode is still connected this way. Anode is still at the top. I cannot flip the circuit connection. I cannot modify it that way. So anode is still at the top. So if I'm measuring diode voltage, the positive reference is always at the anode, negative at the cathode, meaning plus will be at the top, minus at the bottom. If it's an open circuit and I measure the voltage at the open circuit, I would get 10 volts or plus 10 volts, which is basically my power supply. But my assumption is the diode is off. And if the diode is off, VD must be negative. Since I'm obtaining a positive number, my assumption is incorrect. And of course, this is like a Thevenin equivalent circuit, so it's rather easy or straightforward to analyze. Right? We have an anode connected to positive of this, so automatically we think on. But oftentimes we have multiple diodes in a circuit, and the more diodes we have in a circuit, the more complex the analysis becomes. So after the next two slides, I have an example with 3 diodes. And so we'll go through analysis by making a wrong assumption at the beginning. Okay. So this same example in a constant voltage drop model. So I'm going to assign for student practice using the same techniques. All you would do is you would have a voltage source of plus 10 volts here. You have a resistor of 10 kilo ohms and assume that the diode is on. And so you'd have a constant voltage drop of 0.6 volts applied right there. And if you're assuming D is on, that means you must have a positive diode current ID. Positive diode current. So solve for ID and see if your assumption is valid. Reverse bias, if you assume the diode is off, it's the exact same analysis as the ideal diode. That doesn't change. It's only the forward bias that changes. Okay, so it's one step Ohm's law answer. And the answer is here on the next slide. We analyzed the same circuit using load line, and we obtained a current of 0.94 and a voltage drop of 0.6. There would be some fluctuations or variations between different people, right? Depending on how far in you can zoom into the graph. If the graph is zoomed in into the intersection point, we could get 0.65, 0.67, right? 0.58, 0.59, more precise, more accurate values, more accurate numbers. So these were just, again, this is a solved example. So you know it's 0.94 and 0.6 volts using the graphical method. The mathematical or the iterative analysis resulted in 0.941 and 0.592. I went up to 3 decimal places in the iterative analysis that I showed on the slide. Within, let's see, 0.592 here, within 2 steps. I would even say technically 1 step. I obtained a match between my assumption and my answer. And so 0.941, 0.592. Ideal diode is obviously the most imprecise or least accurate, not precise, but least accurate of all, simply because we are using an ideal device, right? So the voltage is going to be far off. The current, however, if you notice, is not that far off. 0.94 to 1. It's a difference of 0.06 milliamps. That's only 60 microamps. So even though my diode values are off, which I would expect, it's an ideal diode, my current values are not that far off using an ideal diode model. But that's not the reason why we use ideal diode model, and I will explain later. And then constant voltage drop, 0.94 and 0.6. So you can see there is a very close alignment between these methods. So it's 4 different methods. Technically, technically it's 4 methods, but ideal diode and constant diode, I just merged them as one technique. So 3 different techniques, and all results are very closely aligned. Okay. All right, let's take a pause. Let me know if you have any questions. Do the steps make sense? Okay, so, oh, sorry about that. Let's turn it off. Ideal diode model is my go-to model when I want to perform a quick analysis of any circuit. Okay, if I want to do a quick analysis of any diode circuit, not necessarily determining the voltages and currents, but just an analysis on how a circuit operates, I use ideal diode analysis. And in just a little bit, we'll look at like diode rectifier. Well, it's 11:30, so we may or may not be able to get to it. But once I explain that, I'm going to use the ideal diode model to actually explain the operation of these diode circuits. There are a couple of things, a couple of quantities I wanted to point out. First is static diode resistance. Also known as DC resistance. And static or DC resistance for a diode is simply the resistance at the operating point or the Q point. And simply RD is equal to VDQ or IDQ. And that's it, at the Q point. Okay. So if you have a diode characteristic, it goes like this. And this is the Q point. This is VDQ. And this is IDQ. So VDQ or IDQ gives you the DC resistance or the static resistance at that operating point or that Q point. Obviously, the Q point can move up or down the line depending on the applied source voltage, right? It can move up and down anywhere on the diode characteristic. If it's in the on region, the resistance will be lower. If it's in the off region, meaning before the forward voltage drop is applied, it's going to be higher. Or in reverse bias, it's going to be higher. Yes. VDC. No, it's diode resistance is equal to diode voltage at the Q point divided by the diode current at the Q point. So it's known as DC resistance because it's one single point, it doesn't move anywhere. Remember, the Q point is dependent on the source energy. But once the source is fixed, whether it's 5 volts or 10 volts or 15 volts, the Q point for that diode is going to be fixed, meaning the operating point, the diode is fixed. It's not going to move, right? Yes. Yes. So RD is the internal resistance of the diode. Again, overall, the diode is non-linear, but there are some portions that are linear. So we can apply some linear equations to some quantities. And if you recall the PSpice simulation for the diode in the lab, one of the quantities we specify is RS. RS is the series resistance. And so the diode is modeled as a diode in series with a resistor, like an inductor or like a capacitor. You have a resistor that's internal resistance. It's not physically separate, right? It's part of the component, but we represent it as a separate electrical resistance. Yes, and then do you have a question? Okay. Yes. Yeah. Okay, and then there is dynamic or AC resistance. And as the name suggests, we pick a point or 2 points in there. To determine our AC resistance. But there's a whole technical explanation that we can't get to into this class. So the diode curve is not technically a completely flat or linear line, right? So there is some curve to it. So mathematically, we can draw kind of like a tangent to that point. So we pick a point and we pick minor variations of the voltage on either side of that point. And so let's say I apply an AC signal and I have a Q point of the diode from the DC biasing. Now I apply an AC signal on top of it. How much is that Q point going to shift? So let's say this is the original Q point from the DC voltage. So I have VDQ and IDQ. And then we apply an AC input to our diode. So this would be delta V. This would be delta ID. And so then the AC resistance of the diode this subscript D is for diode, not for DC. So RD AC, or static and dynamic resistance, and there's a brief mathematical derivation where we can prove this comes out to be VT over ID. So this is the variation in the diode voltage it turns out to be the thermal voltage divided by ID. And that ID depends on whichever point you take. So if it's the Q point, it would be IDQ. If that Q point changes, it would still simply be that fixed value of ID at that point. The thermal voltage VT over ID. Okay. And these two equations are something you would need for lab 3 calculations. How many of you have? My lab is today. So how many of you have labs on Monday or Tuesday? It's not on Monday and Tuesday, right? It's just Thursdays. Question or no, 346. Is 346 scheduled on Monday or Tuesday? Anyone? I haven't looked at the schedule. Anyway, so lab 3 is yet to come, right? For everyone. Okay, so now let's take a look at an example with 3 diodes. In the interest of saving time, I have my annotations written out. Yes. It's not called, we can model it as a resistor, yes. So the question being asked is, what is exactly RD? What is the resistance, right? So any device, if you apply voltage or supply an energy, is going to allow current to flow through. I mean, if it's a conducting device, right? But it's not an ideal conductor, meaning current cannot be infinite. There is some opposition to the flow of that current. Even a metallic conductor, let's take gold, for example, one of the best known conductors of electricity. Okay. Even that conductor is not ideal. We can model that conductor as having some resistance. So in that same manner, any device that we have, whether it's a diode or a transistor, an FET, any kind of electronic device, will oppose the flow of current. And that opposition can be modeled as that resistance. And that's the series resistor RS of the diode. Typically, it's very small. In the PSPAC simulation for the lab, it was like 1 ohm. Okay, we only had it as 1 ohm. So it's going to be very, very small, but that's where it comes from. Does that answer your question? Okay. All right, so multiple diodes. What do we do when we have multiple diodes? Well, so 3 diodes, D1, D2, D3. If we use ideal diode model or a constant voltage drop model, we can replace it with a short circuit in the forward bias and an open circuit in reverse bias. So here, I'm going to use constant voltage drop model. In the constant voltage drop model, sorry, let me silence this. We are going to model it with 0.6 volts in the forward bias. Okay. So constant voltage mode, we can analyze this with the ideal diode model also, but I'm going to choose constant voltage drop model. Now, depending on the number of diodes, our analysis changes depending on the number of diodes present in the circuit. In the previous circuit, we only had one diode. So there's only two possible states, either on or off, right? So there's a maximum of only two analyses that we have to perform in case our first one is wrong. Make sense? So the number of possible combinations is 2 raised to n, where n is the number of diodes. If you have two diodes in a circuit, 4 possible combinations, 3 diodes in a circuit, 8 possible combinations, 4 diodes in a circuit, 16 possible combinations, and so on and so forth. Okay. Now the combinations basically meaning if I assume a diode to be on or off. In this case, there are 3 diodes. If I assume all 3 of them to be on, that's one combination. If I assume all 3 of them to be off, that's a second combination. Or I can assume D1 on, D2 and D3 are off. That's a third possible combination. And then D1 on, D2 on, D3 off, so on and so forth. So 8 possible combinations of the diodes, meaning I could go through 7 different analyses and all of them might turn out to be incorrect. And I would have to do an 8th and final analysis to see if that works. Make sense? Right? Obviously, your job as an engineer is to make a guess, but it should be an educated guess. So you make assumptions onto the state of the diodes in our circuit, but we'll base those assumptions on certain logic, right? If the anode, if we inspect a circuit and we feel the anode is at a higher potential than the cathode, then logical conclusion and the assumption would be that the diode is on, right? And so if we inspect the circuit, if I inspect the circuit, I can see, let's see, there are 3 points that I've noted, A, B, and C, where the diodes are connected, right? So if I look at diode D1, the anode of D1 is connected to plus 10 volts. Obviously, it's also connected to minus 10. It's also connected to ground, but there are other diodes in the picture. But the most direct possible connection is directly through resistor R1. So anode is plus 10, cathode is minus 20. Logic dictates that more likely than not, diode D1 should be on. So I'm going to assume that D1 is on. Same thing with D2. D2's anode is connected to plus 10, cathode is connected to minus 10. So again, logically, I would think that D2 is also on. So I make that assumption. And then D3, anode is connected to ground, which is 0 volts, right? And cathode is connected to minus 10. So again, logically thinking, I would say D3 is also on. So my first assumption, my first analysis, I would choose all 3 of the diodes to be on. Make sense to everyone? So my first state, I choose all 3 of them on. So D1, D2, and D3, all of them on. And then I'll replace them with 0.6 volts voltage source in all 3 places, because I'm using the constant voltage drop model. Right? Ideal diode model is exactly the same, except it's easier to analyze. All right. So now I would perform circuit analysis based on these voltages, and I need to determine the diode voltages and diode currents. If all diodes are on, that means all diode currents must have a positive number, positive value, right? That's the key thing. All diodes are on, so all diode currents must be greater than 0. It cannot be 0, it cannot be less than 0, meaning it cannot be a negative number. So now we just perform circuit analysis on this. And that's it. Okay, no matter what kind of circuit you are faced with, in the end, it's the same 3 techniques: Ohm's law, KVL, and KCL. Okay, so here I'm going to label these currents first. I have ID1 because the anode is on the right. ID1 goes towards the left. Because anode is on the left, ID2 goes towards the right. And here for D3, anode is on the right, so ID3 is going towards the left. Okay. And I'm just going through the logical steps of circuit analysis. So I first make an assumption, then I replace the diodes based on those assumptions. Then again, based on those assumptions, I'm going to outline the diode voltage polarity and the diode current directions, right? So if you take a look at ID1, ID1 is the same current that's flowing through R2. So ID1 is the same as IR2 in series. So if I find IR2, I get ID1. In the same manner, I can find IR1 through here. Once I find IR1 and I have ID1, I can find ID2 by applying KCL. Right? At every single step, my job is to ensure that when I write an equation, there should be only one unknown variable. And then I solve for that unknown variable, then I write a second equation using those values. So I'll take a look at the voltages at A, B, and C. You apply, since I want to find voltages, since I want to find current, I need to apply Ohm's law. For Ohm's law, I have the resistor values, but I don't have voltage. So in order to find voltage, I'm going to apply KVL. Yes. I will explain. Actually, it's not an assumption. It's a calculation. So node A is 0.6 volts less than point B. Node B is about 0.6 volts higher than node C, right? Plus minus. And node C is 0.6 volts less than ground. So VC is minus 6 volts. VB is 0.6 volts higher than C. So it's 0.6 higher than minus 0.6, effectively comes out to be 0. And then node A is 0.6 volts less than node B, so minus 0.6 volts. Make sense? It starts from the right, and then it goes towards the left. Yes. We'll check the answers. So this analysis is wrong. Not, I mean, the analysis, sorry. The analysis is correct. The assumption is wrong. So I chose this on purpose. Okay. So we don't know until we look at the answers at the end. Okay. That's why the methods for electronics are numerical. We don't always arrive at the right answer just by using one model. We use multiple different models or multiple different techniques or multiple analyses within each technique. All right, let's see, 11:51. Let's get through. All right, so everybody's clear on VA, VB, and VC, right? And every circuit is different. Every circuit is different. All right, so once I have VA, VB, and VC, I can find IR1, right? IR1 is right here at the top. Since I know node voltage at VB and I know voltage here is simply 10 minus 0 over 10,000. So IR1 is 1 milliamp. Okay. Then I know the node voltage at A, and I know the voltage across R2 would be VA minus or minus 20, right? And so that would become minus 0.6 minus of minus 20 divided by R2 gives me 1.94. Now, IR3, same manner, is node C minus of minus 10, right here. It gives me 0.94 milliamps. From these three resistor currents, I can find my diode currents. ID1, simply the same current as IR1, so 1 milliamp, which is greater than 0. So my assumption for ID1 is correct. ID2 is IR1 minus IR2, gives me minus 0.94 milliamps. So that is incorrect, right? I assume my diode to be on, so the current must be positive, but I obtained a negative number. That's how I know my answer or my assumption was incorrect. Make sense? So this marks it incorrect. And then once you have even one quantity or one diode state to be incorrect, the entire assumption is incorrect. Okay, so you don't need to find, I don't need to find the third one, but I'm going to go through it anyway. The third current is ID3, get a positive value, 1.86 milliamps. So my assumption about diode D3 is correct. I want to be very clear. My initial assumption was on. Okay, on. If a single diode assumption turns out to be incorrect, the entire analysis, the entire assumptions for all three of them are incorrect. It doesn't mean that diode D1 and D3 are on. Okay. In the end, it might turn out that D1 is also off, D2 is also off, and D3 is the only one that's on. So if even a single diode from your assumption is incorrect, that means all three assumptions are incorrect. It means when you analyze, it doesn't mean that you just change one. You have to change multiple states. So be clear about that. Yes. So the question being asked is, can I just change D2 and then perform an analysis? And that is going to be my next logical assumption. But again, as I said, it doesn't mean that it's going to end up correct. Again, I solve it for D1, D2, D3. I would change D2 to off, D1 and D3 on, and I'll perform my analysis. And that state might also turn out to be incorrect. At this point, we don't know. Okay. But if even one diode is incorrect, you throw out the entire assumption. You simply cross a line through it. There are 7 more assumptions still to go. Yes.
Why did we find the second diode current?
So right here. So the question being asked is, how did we find ID2, right? So ID2 is here. ID2 is here. So I applied KCL at this node. And so IR1 is coming in here and it's splitting into 2. And so I found ID2 just by doing IR1. Yeah. So, and I might, I like to keep repeating the same thing again and again. All my classes, basically, I keep reminding students, there's only 3 principles and 3 equations that we use for everything. Ohm's law, KVL, KCL. There are no other techniques that we use. These are the 3 fundamental ones. Okay. All right, 4 minutes left. So I'm going to go change my assumption, and now I'm going to assume D1 and D3 on and D2 off. Okay. And again, this might also turn out to be incorrect. We don't know. So if that's the case, then my circuit is broken up. Right here, D2 is off. So now it's 2 separate parts. Right? This part is completely in series. And so is this. Make sense? Right? And so this becomes rather simple or straightforward. IR1 goes through the diode. It also goes through R2. Same current because it's series. Same thing on the other side. ID3 is the same as IR3 because it's series, one complete loop. And so this makes it rather straightforward. So I apply KVL around this loop like this. And I obtain this equation right here. Because it's a series connection, all 3 currents are the same. IR1 is the same as the diode current. ID1 is the same current as IR2 right here, right? And so I replace IR1 and IR2 as my diode current ID1, and I solve for ID1. I obtain a positive number, 1.47 milliamps. So diode D1 is on. Assumption is verified. Then ID3, which is this current, is going down here. So ID3 is equal to IR3. Again, simply apply Ohm's law. I get minus 0.6 minus a minus 10. If it turns out, I get 0.94. So diode D3 is also on, 0.94 milliamps. And then I apply KVL to determine VD2. There are two possible pathways. I can apply KVL in this path, or I can apply KVL in this path, right? If I apply KVL here, I need to find the voltage across R3 also. So choose either one. I chose this one because it's one less voltage I need to find. So I applied plus 10 at the top, minus 10,000 IR1, minus VD2, and minus of 0.6 should sum up to 0. I solve for VD2. Turns out to be minus 4.1 volt, negative voltage, which matches my assumption that diode D2 is off. So I don't need to do 7 more analyses. Just one more analysis and I'm done. So I'm going to mark this. This is correct. This is correct. And this is correct. Hence, this assumption is also correct. Yes. So I applied KVL right here. Let's use, let's just stick with red. So a question being asked is about this equation, right? Which one here? No, because the anode, so if you look at the circuit, anode is on the left. So the anode is on the left, diode voltage is always positive at the anode. And that VD, because I'm assuming it's to be off, that VD must be negative. If it turns out to be a positive number or zero, or I mean positive number, then it's not off, then it's on. That means my assumption would be incorrect. I would have to redo, I would have to choose a third assumption, and I have to do that. And so there are 6 other possible combinations. Six other possible combinations to enhance your understanding. I would suggest you pick at least 2 or 3 more assumptions of diode states and solve them. Or you can pick all 6. Okay. All right, so we are over time. I'm going to end right here. If you have any other further questions, feel free to ask. I'm going to end the class right here. So again, please practice this circuit. As I said, you know, you already have the answer, so you know which state is correct. Just pick any other two and do student practice. Yeah.